Okay, so let's go through the most kind of basic enzymatic reaction, but let's use the fast equilibrium assumption instead. And as I said before, fast equilibrium, the mathematics for finding the product formation rate, it ends up being easier and less rigorous compared to using the quasi-steady state. So what you want to do for the fast equilibrium assumption is that you assume that the forward and backwards rate for the reaction where an enzyme substrate complex is formed, you assume that they're equal. And you do this for all of the complexes that you have. In this case, we only have ES, so we only have to do it for that. Okay, and we can find ES from that. Okay, and we make the product formation rate, but we still need to use enzyme conservation because we don't want free enzyme to be part of the equation. We want the equation to only have a substrate as a variable that you can manipulate. Remember that E naught is a constant. And here it's easy. We just have the E free enzyme and the enzyme substrate complex. Remember that all of the E must come from this E naught by conservation. And we'll get that. You'll have to work out the math, but this is what you'll get. Okay. And we substitute this back in. Let's make sure everything else is good. ES is -1 there. And we want this form. We want V equals VMS over. We want the Michaelis Menton form. So what we can do is we can see if we can manipulate it to get that form. And this looks like it's going to be very easy. Let me see. I just want to check some of the math behind this quickly, see if I did this. Yep. I forgot to put a K1 on the top. That's what happens if you try to do it too quickly. I kind of jumped the gun here. Let me show you in a few more steps what you can do. What you want to do is we want to get this form, so you'll see that we have to divide both sides by that. And we multiply that inwards. And so what we end up doing is we divide both the numerator and the denominator by K1. And you'll see that it cancels out there. And then we'll get the general Michaelis Menton form. And you'll see it's a lot easier than using the quasi-steady state assumption. And in general, this is actually what we use more often. We always just say, in general, the maximum velocity is just K2 E0. It makes it easier. We don't actually have to really use quasi-steady state that much. And you'll see that this is actually what we got before with the quasi-steady state assumption, except now it's just less generalized. You can take the results from the quasi-steady state and apply an assumption to reduce those into what we get here. So this is the less generalized form. If we go back in history, and if you actually read the papers where Michaelis Menton Kinetics were discovered, you'll actually see that this assumption is what Michaelis and Menton used to get these equations. But the thing is that later someone called Briggs came, and Briggs basically, he made a different assumption, which is called the quasi-steady state assumption, and Briggs was the one who actually found the more generalized form. But we still call all of it Michaelis Menton Kinetics no matter what. But it's interesting because Michaelis and Menton actually found the less generalized form first, and then someone else came and actually made the more generalized form. But that's like a very old paper. I think that was found way back in like the 1920s or so. It's very old. And I know that when I was reading the original Michaelis Menton paper, it was actually translated from German into English, so there was a lot of translator's notes. It's kind of like when you watch an anime or you play like a game that has an awkward translation. So I was reading this technical paper and it had an awkward translation, and I'm like, okay. So yeah, fast equilibrium assumption. It's very easy, and yeah, if you're asked on a question to find the product formation rate, and you're told you can use any assumption you want, use. And if you know the prof is just, if you can use either method, yeah, just go with the fast equilibrium assumption. It makes the math a lot easier. I'll try to do some practice questions that have more complicated enzymatic reactions too in the future. Maybe I'll do some of the ones with the different kinds of inhibition. Okay, well, hope you enjoyed the video.